Okay, so we'll be talking about position space wave function. So we know now that for any arbitrary state alpha, you can use the identity and so this particular inner product, this is what is referred to as the wave function. So we write psi subscript alpha so this is called wave function in position units. Which we are indicating here. So it's basically a number or complex number. Right. So let's try to see the overlap of two different functions, two different states, alpha and beta. And let's use the identity. So what we are going to do, so we have referred to this alpha x prime as psi alpha. So if this is reversed now, we will be referred, this is going to be, since this is a complex number, this will be a complex conjugate. So So we find that the probability amplitude this is independent of the representation. So if I start with state alpha, if I want to check what is the overlap of the state alpha with some state beta, how do I do this? I take inner product and I have to represent them in some basis. So I use identity and represent them in position basis or coordinate basis. And I see that it comes out like this, psi star psi, which we have seen in a lot of books. But now you know the reason that identity or completeness relation is the reason that you get such kind of integrals when you take the products. So we want to see what is the effect of the translation operator on operator is given by suppose we have a state which is translated by now delta x prime. So how one could have generated this? So why apply this? On some position I can say, if I will do the reverse, you know that will be the complex conjugate of this. Okay, fine. Now if I take overlap of this and this alpha, it will give me a translated state or translated wave function in position basis. So if I take inner product of both the sides with respect to this state alpha, then it will give me this is my state at rest. X prime identity alpha, which is nothing but this. And then there is I delta x bar, delta x prime, h bar will come out, this operator will remain. So I can do the Fourier expansion of this, and what will I get? Let's say I go up to the first order and ignore the second order terms. Then this will be a first derivative. And the other terms, higher order terms, which I have to take away. Just write this in. This both will cancel. Here cancels. So what will be the remaining part? I'm going to transfer this h bar and I on this side. So what will I have? Times this. Remember psi alpha, how do I get it here? So I can again exploit the identity here and get something like this. seems like I have the psi alpha, I have some psi alpha here. So this remaining part, this must give me something like this, h bar divided by I and a derivative. Okay. So from this I can say that x prime e this should be something like this. But we still have an integral which should vanish. No, that has to be the Dirac delta function, which when executed this integral will vanish, and this is your momentum operator in position vectors, or as we have known in many texts, accurate description will be x. So this is your momentum operator in position basis. This is how you do it.